So I'd like to talk today about communicating with anecdotes. This is very much a work in progress, hot off the presses. In fact, we don't even have a stable working paper yet, but if you're interested in seeing more, please do email us and we will get in touch with you.
But I hope you do have anecdotes.
I do have some anecdotes to share. We'll see if you catch them all. So yes, please do contact us if you would like a copy of the paper. This is joint work with Nika Hagtalap, who's at UC Berkeley, Brendan Lucier, my colleague at Microsoft, Marcus Mobius, also at Microsoft, and Divya, who is your very own postdoc at Tel Aviv University. And so we'll be talking about communicating, and I will be communicating with you. Okay, there we go. So communication is in sort of a generic sense. You have a sender, a communicator who's talking to a receiver about a state of the world. And examples of this are prominent in our lives. For example, you could have a newspaper who's talking to readers about current events. So here the newspaper publishes articles, and these articles are some form of communication, and they inform the receiver, being the reader in this case, about current events. Similarly, you could have politicians that talk to constituents about policy decisions. And something that we're not really going to cover here, but I'm very interested in as a potential extension could be like even just you and your family and your friends talking over Thanksgiving dinner about some issues, say veganism. And the reason that this isn't really covered here is that in these this extension that I have in mind, you would have the sender and receiver kind of switching roles, and maybe I as an individual, sometimes I send information, sometimes I receive information, and I get to pick who I talk to and in a sort of dynamic sense. So you can just keep that in the back of your mind, but I think that's an interesting extension of these kinds of models that I'd like to learn more about. So the key features of these examples are that there's some kind of information asymmetry. So the sender knows more than the receiver about the state of the world. And there's also some agency. So the receiver has a decision to make, which is how to act. And her choice of how to act is influenced by her beliefs about the state of the world and, her underlying payoff function, which depends on the state of the world. And also the sender gets impacted by the decision of the receiver. So just to give a little bit more structure to what I'm talking about, so we can go through some preliminaries. We have the sender, we'll talk about the information structure of the sender, which is going to be a signal, which is correlated with the state of the world. And there's going to be a communication scheme. So this is a strategic choice of the sender, is a communication scheme that maps the sender's signal to whatever information they're going to communicate to the receiver. The receiver, on the other hand, has beliefs about the state of the world and is also taking a strategic choice, which is an action rule that maps the communicated information to a payoff relevant action choice. And the interesting point about these games is that the payoff relevant action choice is payoff relevant for both the receiver and the sender. So the receiver can't dictate what the sender can't dictate what the receiver does, but would like to influence it through the information that the sender communicates. And of course, agents are going to try to maximize their utility and expectation over the state and the signal. So here's some examples. We have the example of journalism, and you could imagine that the newspaper here might want to tell us, is trying to communicate something about COVID. And so journalists do a lot of research into COVID and trying to understand the danger of COVID and the effectiveness of masks and this and that. And so they do all this sort of journalistic research. The communication scheme here might be the editorial policy of the newspaper about what sorts of things we're going to publish or not. And the reader then is thinking about, how dangerous is COVID and what is the effectiveness of wearing masks and things like that. And then the action that the receiver can take is to decide what fraction of time they're going to wear masks in the world. And here, you know, the communication is the newspapers telling me stuff about COVID, and the reason that the newspaper might want to influence me is maybe, you know, how often I wear masks is going to be some sort of trade-off between personal freedom and global health. And maybe the newspaper has a different trade-off over this than I as a reader. And so the newspaper wants to influence me to wear masks more often.
So here is a good example, Nicole, by the way. It's not just, you know, values health over personal freedoms. Even if the newspaper was CDC, the CDC objective and the personal objective are not the same.
Yes.
So that's a very good example where, you know, what the CDC wants is, again, the overall cost of health, and what you care is your own, and those are different things.
Yeah, exactly. That's a great example.
COVID points it out beautifully, yeah.
I like the newspaper example because of the front page of the New York Times I showed here, which I will return to shortly. But the CDC also might have different like opinions about or trade-offs around this. And, you know, also politicians might have different trade-offs around how often we wear masks, and because like maybe masks impact the economy and the politicians care more about the economy than I do. So there's all sorts of competing interests here. And then we also have politics as a second example. And here you might have a president. And the president is going to learn about stories about some issue, say the gender wage gap, from her constituents. So she'll go around and listen to her constituents. She gets lots of stories about how the gender wage gap is impacting her constituents. And her communication scheme here is her selection of speechwriters who are gonna, like, you know, help her sort of project all of the information she's learned into a, say, State of the Union address. And then the constituents are going to have beliefs about the gender wage gap and like the optimal trade-offs between free markets and fairness and things like this. And the action they might take is how much to pay employees. This example is slightly more forced, but again, you'll see that I selected it because of a speech I found from one of Clinton's stump speeches. And so here again, maybe the president values fairness over free markets more than the employers, and so wants employers to pay women more. And so in these contexts of these examples, we need to decide what is the solution concept. So how is the sender going to decide what information to communicate? And you know, the sender is strategically selecting information to communicate to induce the receiver to take certain actions. And there's two solution concepts I'd like to focus on. The first is Nash, or cheap talk. And here the sender and receiver are simultaneously making their strategic choices, each being a best response to the other. So the sender simultaneously with the receiver, the sender chooses a communication scheme and the receiver chooses an action rule, and then these need to be best responses to each other. And after they make these choices, the signal is drawn correlated with the state of the world, and the communication is revealed, and the action rule maps it to an action. So that's the Nash setting. The other setting that we will discuss in this talk is the Stackleberg setting. So here there's a first mover, and the first mover is the sender. So the sender can commit to a communication scheme, which maximizes the payoff given the receiver's best response. So the sender moves first here. The sender decides for any potential signal that might be drawn from the state of the world, what is the sender going to communicate? And the receiver is then going to best respond to the communication scheme that the sender committed to. And so in order to solve these kinds of games, this has been studied a lot in the literature. So far, I've told you nothing new. But one of the kind of first things people do in order to solve these games is to state some sort of revelation principle like statement, which restricts what the set of schemes is that we need to think about when we try to solve for the equilibrium. And so this principle, I mean, this is sort of very high level. It'll say something like, well, you know, the sender has some communication scheme, and it might be very arbitrary. It might be like, you know, a long essay which starts with, you know, the word the if the state of the world is 10, and starts with the word while if the state of the world is 11, and so, you know, it could be some arbitrary communication scheme, and the receiver is going to take whatever this long essay that the communicator communicated and decide how to act. And we can abstract away from all of that, says the revelation principle, by just wrapping it all into some black box, and the sender can simulate how the receiver would respond to whatever communication she had intended to state, and then just tell the receiver, hey, this is how you, like, I had this communication scheme in mind, this is how you would respond. And so if the sender commits to this kind of black box thing, then the receiver can just take the sender's recommendation at face value. And so there's some sort of element of this in most of the papers on these communication schemes. And this is something we would like to relax a bit with our idea of what's communicated is actually an anecdote and not an arbitrary message. And so I can't just tell the receiver an arbitrary action. So I'll get back to that in a minute. But using this kind of technologies, the prior work has looked quite deeply into these concepts of cheap talk and persuasion, or the Nash equilibrium and the Stackelberg equilibrium. And I'd like to tell you a little bit about that so we can compare our results to this prior work. In the Nash equilibrium, this is again the one where the sender doesn't commit to a communication scheme. The sender and receiver move simultaneously, and sort of the famous results, or like the folklore result here, is that there's this temptation to babble. So in a babbling equilibrium, the sender speaks nonsense. The sender might tell you to wear masks all the time, no matter what the state of the world. And then the receiver ignores what the sender says and just acts based on their prior. And this is always an equilibrium, because if the receiver is ignoring me, it doesn't matter what I say. So babbling is a best response. And the receiver, if I'm babbling, then the receiver has no reason to take into account what I say. There's also a separating equilibrium in which the sender communicates the information, the full information that she has about the state of the world, and the receiver exactly optimizes. So this is a potential strategy profile, and it's an equilibrium if the payoff functions of the sender and receiver are exactly aligned. But of course, they might not be exactly aligned, and then this is probably not an equilibrium because the sender is losing some utility due to telling the receiver everything she knows. And so the sort of intermediate type of thing that could happen here is called pooling, where the sender pools together signals and the receiver takes the optimal action given the pool of signals. So it might be like, I could tell you the effectiveness of masks is between, cuts transmissions rates from 70 to 80% or something like this. I have no idea what the truth is here, but like, I might know as the sender the exact transmission rate given that you're wearing a mask, but I instead group it together into some like range and let you decide how to react given that range. And what Crawford and Sobel says, so this is one of the seminal papers of the game theory literature, Crawford and Sobel, 1982, they say, well, generically we get pooling equilibrium. This is sort of a tautology because I already convinced you babbling is equilibrium, and babbling basically pools everything together. But more interesting, they say that the finest pooling equilibrium is Pareto superior to all others. So the sender wants to communicate as much information as possible. That's the finest possible pooling equilibrium, subject to the incentive constraints, which are induced by the preference misalignment. And furthermore, as our preferences are less misaligned, we can support finer and finer pools and hence better and better equilibria. So that's the cheap talk setting. We also have the persuasion setting, which is the Stackelberg game. And this is in a seminal paper of Comencia and Genskow, in which the sender, they show you that in the Stackelberg game, the sender can also persuade the receiver by pooling. In fact, they characterize exactly when the sender can gain by trying to persuade the receiver with their commitment to their communication scheme. This is an interesting, like, in order to tell you the sort of sense of this theorem, the high level idea of this theorem, I think it's easier to think through an example. So here's an example with a prosecutor and a judge. The prosecutor is the sender and the judge is the receiver. And the prosecutor, the sort of prior on the state of the world is that a third of the defendants are guilty and the uniformly random defendant is brought to court. And the judge, of course, wants to acquit the innocent and convict the guilty, but the prosecutor wants all defendants convicted. So the prosecutor knows whether the particular defendant that was brought to court is innocent or guilty. Can the prosecutor commit before seeing that defendant to a communication scheme that will induce the judge to convict more people than she might otherwise? And we can actually draw this out on a graph. You can put on the x-axis the posterior probability that the defendant is guilty, and on the y-axis the ex-ante probability of conviction before the defendant is drawn from the population. And if the posterior is less than a half, so it's more likely that the defendant is innocent, then the judge will acquit and the prosecutor will have 0 payoff. Otherwise, the judge will convict and the prosecutor will have a payoff of 1. If the prior is 1/3, as I suggested in the previous slide, then the judge will just always acquit because less than half the people are guilty, and the prosecutor will be very sad. But the prosecutor can commit to pooling and thus concavify the posterior beliefs of the defendant in a sense, or pack together different states of the world, basically, do some clever pooling in order to concavify this function and thus induce the judge to convict some of the defendants. And so I haven't put a lot of time into explaining this example to you. I encourage you to read this paper because it's a really pretty paper, but the point that I want to get across is that this orange function here, the sender's expected value given the receiver's posterior belief and action, is not concave. And so what Comenska and Genskow say is that the sender can gain from this sort of pooling type strategies when this function is not concave.
I must, as I always do in this kind of talks, since some people may not know it, all this is Aumann Maschler in the 60s, dressed up in a nice story, but the idea of the concavification and pooling and all this, exactly like this, Aumann Maschler, 1960s, in the 67 or some 66, 67, just for the reference, before everybody will forget it.
Thank you. Yes, we will make sure to cite the correct set of papers. Yes, so beautiful, beautiful stories, I think. And so now so that's what's been done in the past. Let me tell you now about what we do. What we do is we want to take very literally the idea of how people communicate. So far I've said there's some arbitrary signal correlated with the state of the world, and the sender can say anything that she wants. But what I really think happens in the world is that this signal isn't arbitrary signal correlated with the state of the world, but rather a set of samples drawn from a distribution that's a function of the state of the world. So far, I haven't said much, but I want to think about these samples as being anecdotes. So stories or examples of, say, like how often people wear masks. I can get some examples for how often people are wearing masks by reporting on, say, an opera and how everybody attended the opera without masks and stuff like that. So anecdotes that are based on the state of the world. And I'm not going to have time to really emphasize this, but in some worlds, we also imagine that the sender has foresight. They might even know the state of the world exactly, but still they can only communicate anecdotes. And then the communication schema here is that I get to pick a single anecdote to tell the receiver. So here's why I picked my two examples earlier on, because I think that it's like this is sort of intuitive to us that we communicate anecdotes a lot. But here in these examples I drew upon, I think you can see it very clearly. So here, this is the very famous front page of the New York Times from May 2020, during like, you know, one of the waves of COVID. And the New York Times, the entire front page was just a list of deaths of 1,000 people. Like we had reached in the US 100,000 deaths from COVID, and the New York Times listed 1,000 of these names on the front page. So these are, like, if you like, 1,000 anecdotes about the danger of COVID. Here's another example from the political sphere, and this is an actual Trump speech of stump speech of Clinton. And so she would talk a lot about this anecdote where she saw two young people who were 17 years old, a man and a woman, and they were doing the same job, and one was being paid $8 an hour and the other was being paid $15 an hour. And this highlighting is actually not my highlighting, but the NPR, a radio program in the US, did an analysis of Clinton's speech and pointed out how much she relies on anecdotes here to get her message across. So those are two examples where we see a sender communicating anecdotes to a receiver. And so how does this actually impact the style of results I told you about before, the revelation principle style result, the Nash equilibrium, and the Stackelberg equilibrium? What gets communicated and how, and when we can only communicate with anecdotes? And the first theorem that we'll see basically says that when communicating with anecdotes, the optimal scheme is going to send an anecdote that's closest to a shift of the posterior. So I don't have to think about all sorts of possible things to communicate given anecdotes. Like any possible subset of anecdotes is something I could send. But as a sender, all I have to think about is what anecdote is closest to my belief, given what I've seen. Yes?
All your examples, I want to know, is the payoff of the receiver state dependent or independent of the state?
It's state dependent. It's going to be like Crawford-Sobel. Yeah.
It is state dependent. Okay. Yeah. Thanks.
So this first theorem here, I think, is already teaching us something about the world, or like it's intuitive given the world, in that I'm not trying to say, like, when I decide what to communicate as a sender, I'm just trying to decide how biased I want to be, how much I want to shift. And then I want to find some story that's consistent with that bias. And I think as receivers also, we think about this a lot. We think, well, the New York Times is slightly left of center, and they're communicating things that are slightly left of center. And we take that into account when we read the New York Times or listen to Clinton's speeches. Yes?
Sorry, another question. So assume that the set of anecdotes is the full, is everything. Okay, then it means no shifting. Then the closest anecdote is just the truth, right? The true state.
Well, this is to a shift of the posterior. So I haven't yet said how the sender selects the shift, but it'll be the closest anecdote to a shift of the posterior. So it might not be the truth.
But a shift, sorry, I guess I now understand even less. What's a shift of a posterior? Everything is a shift of a posterior, no?
Yes, so this isn't a specific scheme. This is a class of schemes, which is parameterized by this shift parameter. And I might decide I'm going to give you an anecdote that's left of center. It's like, the closest anecdote that's, one standard dev less than the mean. that I believe about the state of the world. I'll make this more precise later. I'm just
Okay.
trying to, yeah, maybe it's better.
Yeah, I'm still puzzled. Okay.
Yeah, I know.
But I'll wait. It's still, yeah.
It will give you some mathematical formulas about this. We then see that without commitment, so in this sort of Nash equilibrium setting, the equilibrium scheme is biased. And the shift of the scheme is going to grow as the preferences of the sender and receiver diverge, or as the number of anecdotes grows. So this will be interesting to you later, Sergio, when I make things more precise. And the third result is going to be in the commitment case with the Stackleberg setting, the equilibrium scheme is unbiased and asymptotically at least sends the anecdote closest to the posterior. So just to compare a little bit to the Crawford-Sobel and the persuasion literature, in both in our paper and in Crawford-Sobel, when you can't commit, so you're doing some sort of Nash equilibrium, you're getting less than the best possible amount of information that you could communicate. So Crawford-Sobel is saying like there is pooling, which means that the sender knows more than they're able to communicate in the Nash equilibrium. And we also get some bias in which anecdote we're sending, which therefore induces higher variance. And so we're also communicating less, like the variance of what we're saying grows as when there's differences in the preference structures. And compared to the Stackelberg or persuasion literature, we are basically, I showed you how we need this value function to be concave. And what we're saying is that like our value function is basically concave. And so we're consistent with that literature and sending the unbiased anecdotes. So let me move into telling you a little bit more detail about the model so that we can talk more precisely about what's going on. I just wanted to mention again this related work of the cheap talk and persuasion literature I've already mentioned. I also think that there's a sort of deep relationship between our paper and the voluntary disclosure stuff, because voluntary disclosure literature is saying we can only communicate facts. So there's a set of facts and I can't manipulate the facts, but I can decide which ones to disclose. And so there's a long line of literature looking at that kind of stuff, which I will skip for in the interest of time, but basically, you know, it says sometimes we get full unraveling and sometimes there's partial unraveling, and you can read about how our work relates to that in our working paper. So let me tell you the model. We have a sender and a receiver, and there's a state of the world. I'm going to assume the state of the world is drawn from a diffuse prior, so it's equally likely to be anywhere. And then the sender and receiver each have an ideal shift from the state of the world. So, you know, the state of the world here might be the danger of COVID or the effectiveness of wearing masks. And you know, you can project that onto anecdotes, which are how often people wear masks given that state of the world. The sender wants the people to wear masks a bit more, say, so there's a shift MS from the state of the world, and the receiver wants people to wear masks a bit less, so there's a shift to the right from the state of the world. So here MS I'm thinking of as negative. And then anecdotes are drawn from this state of the world. They're drawn IID, and we're going to assume that the distribution is single peaked and symmetric around the state of the world. And let's say that there's K anecdotes drawn. We can talk about what happens as we take K to infinity, but for now we have a finite number of anecdotes K that are drawn from this prior that's parameterized by the state of the world. The actions in this game, the sender is going to pick a communication scheme, which is a function that maps the set of anecdotes that were revealed to a chosen anecdote that will be sent to the receiver. The receiver is going to select an action rule, which maps whatever anecdote she receives into an action that she's going to take.
who sees the set of anecdotes? Only the sender,
Great,
the
yes.
receiver,
So
both?
the anecdotes are only seen by the sender, and
So the receiver only sees the chosen anecdote from the set that is seen only by the sender.
Yes.
But the communication scheme of the sender is known by the receiver?
So this depends on the equilibrium concepts that we are going to, if we're in Stackelberg, so the sender can commit to it, then the receiver knows it. If we're in a Nash equilibrium, then the A has to be a best response to pi and vice versa. And the other thing that I didn't mention, I should put it on the slides, is that these shifts, MS and MR, which we named M because we were thinking of them as moral stances at some point, but these M's are common knowledge.
And fixed. So it's always, regardless of theta, it's always the same shift.
Yeah. And this, in case you're interested, is like the Crawford-Sobel setting with, but their MR is 0. Here, I thought the story was a little bit nicer if it's a bit more symmetric. So that's why I put MR as a parameter.
It has a more morale.
Yeah. So the payoffs, we're going to focus on quadratic loss, which is one of the primary examples in Crawford-Sobel, although they also generalize to general convex functions. So the sender wants the action of the receiver to be close to their ideal shift of the state of the world, but this and they suffer quadratic loss as the action drifts away from their ideal point. And the receiver similarly wants to take an action that's close to their ideal point and suffers quadratic loss. And so this is a functional form that's very easy for us to work with. We would love to generalize this to arbitrary convex functions. We're working on that, but I don't quite know how much we can generalize this. I believe the sense of the results should still hold, but we don't have that result. So these are the utilities. And the equilibria, as I've mentioned, we're going to focus on the Nash. So here, pi and A are an equilibrium profile if each is a best response to the other. So the receiver's action is maximizing the receiver's utility given the communication scheme of the sender. And the sender's communication scheme is maximizing the sender's utility given the action rule of the receiver. We also will be talking about the Stackleberg setting, in which the equilibrium profile pi and A, which can be dependent on pi now, is an equilibrium if given the communication strategy pi, the receiver is best responding to it, knowing it. And then the sender picks the communication scheme that maximizes her utility given that the receiver will best respond to the sender scheme. So let me introduce some preliminary results that will help us talk through the equilibrium results. And so what I want to do now is make this informal theorem we discussed a little bit more precise. That the optimal communication scheme sends an anecdote closest to a shift of the posterior. What does that mean? So here we have our setup. We have our sender, receiver, there's some anecdotes, a state of the world, and if the sender doesn't have foresight and so doesn't know the state of the world, then the sender has some posterior theta S base, because like the sender sees these anecdotes, so they've formed some posterior belief about the state of the world, theta S. If the sender knows the state of the world, you can just set theta S equal theta. And so what could the sender communicate? She has to have some function pi that maps these anecdotes to one that she's going to send. And so one potential...
What is theta S is a point estimate, but there are many, I mean, this is not uniquely defined.
What is not?
From the theta S. I mean, you're assuming, I mean, there is a distribution, but not what's theta S. It's a best something mean square, or I don't know, some specific estimator, right?
Yeah, I was thinking of it as the mean of posterior belief, the mean of the posterior.
Mean, okay. So it's a Bayesian mean. What's called the Bayesian mean. Okay.
Okay. And so the one communication scheme might be.
And you probably can show that that's the only thing that matters, only the mean. The distribution doesn't, because of the quadratic, you probably can show that whatever you do with the full distribution, you can do with the mean.
Yes,
okay.
Exactly.
Good. Okay.
And so communication schemes might be, I could send the minimum, so this is a potential communication scheme. Any set of anecdotes I receive, I'm going to always send the minimum. Another one would be, I'm going to send you the anecdote that's closest to the mean of the posterior. And another one is maybe I'm going to so something that slightly generalizes that second example is I'm going to send you the anecdote that's closest to a shift of the posterior. So I pick a parameter R, I pick a shift R, how far do I want to shift my posterior before I tell you what anecdote I'm sending. So I pick R and then I send you the anecdote that's closest to that shift. And so Nicole, these are three, yeah.
Are you restricting attention to schemes where you send a single anecdote?
Yes.
What about? And this is, I guess, with loss of generality, right?
This is with loss of generality. I think if you want to send a subset of anecdotes, in the Stackelberg case, you'll send the subset of anecdotes that communicate the most possible information, that give the receiver the most possible accurate beliefs about the theta at the end of the day. And with the Nash setting, I think things might be a little weirder. I don't quite want to commit to what it'll be.
Okay, thanks.
So what we want to say is that the anecdote that's closest to the shifted posterior, that third example, is this only sort of scheme that the sender needs to think about. So the sender's choice is really just what R should I commit to, or what R should I pick? What should my shift be? And so in order to give you a sketch of the reasoning for that.
And is it clear that R should be independent of theta S? Should be a constant? In principle, you could, for every theta S, you could have a different R, which means theta S hat or something. Is it clear that a constant shift is optimal?
I was hoping so. I believe that's without loss of generality in this world where the ideal point, so it's going to depend on my ideal point, which is a shift from theta, but because the prior is diffuse, I'm leveraging that. So the prior over the state of the world is diffuse, then there's no real meaning to any specific number that comes out of this world. And so any scheme has to be translation invariant. And hence R shouldn't depend on theta.
I'm not sure if theta is very extreme. Suppose that you got anecdotes that are very much to the right, and then theta S is very much to the right. Maybe you want to correct it more than when theta S is close to the middle or close to the left.
But to the right of what? Because you don't know theta.
You have a normal distribution, I guess, of right, with some mean, or theta or theta.
We want to say that the anecdotes are drawn from a single peaked symmetric distribution.
Okay, normal. Let's take it normal. Yes.
Say normal.
Okay.
But you don't know the mean of this normal distribution.
Yes, that's theta. That's the unknown theta.
Right. Right.
Okay, but still, but there is a prior on theta,
which is diffuse. So any theta is equally likely.
Any theta
this isn't entirely formal because
but
I have to formalize
set.
what I mean by a diffuse prior, but
you have a problem because you can't do it on the whole line, so you have to do it on a limited set, and then you have problems at the boundary, and so there is some inconsistency here.
So there's definitely something to formalize. If this is super bothersome, we can always talk about just translation invariant schemes in which we impose this as a condition that this R is not a function of theta, which is the way we're currently writing it. But when I was preparing this talk, I thought I should be able to get this result. So
okay.
So Nicole, a quick question. Don't you want the anecdote to be such that after the receiver updates her belief, the shift will be closer to theta S? Or is it the same as basically this anecdote that you suggest?
Yeah, it'll be the same. So because what the receiver is going to do is undo the bias of based on the shift. So let me go a few slides and see if you still question this. But when I decide what the shift is going to be, then I can define the bias of this scheme. So any scheme, of course, has a bias, which is how far off the anecdote is from the posterior belief of the mean posterior belief of the sender. And notice that this bias is going to be, because the distribution is single peaked and symmetric, the bias is going to be slightly less than R itself. So we can define the bias to be this expectation, like how much to the left of theta is in expectation is the closest anecdote to that shift. And then the receiver is going to have a best response, which is, and this is, I think, answering your question, Moshe, the receiver is going to, I'm going to, of course, in equilibrium, the receiver has a correct perception of the bias of this scheme pi r, but I'm going to keep it as a separate parameter right now. So the receiver has some belief about what the sender's scheme is, call it pi r, and that believed scheme pi r has some bias, and the receiver is going to look at the anecdote that is sent and is going to debias it by shifting it back to the right, and then is going to add their ideal shift MR, and that's going to be the action that the receiver selects. So for example, the receiver, if they were completely naive, they would just take the anecdote at face value and believe that that was the state of the world. But in fact, they know that this anecdote is biased. And so what they're going to do is they're going to think about, well, what is the bias of the scheme? And then they're going to debias the scheme by shifting their posterior to the right. And then they're going to choose an action that's their ideal shift from their shifted posterior. So this now shifted posterior is debiased. It's an unbiased estimator of theta. And so what the sender wants to do, so that's what the receiver is doing, and what the sender wants to do is pick what to communicate in order to minimize the squared loss. And so the quadratic loss. And so there's several things that are sort of preventing the sender from, that are, pushing back against the sender here. One is that the sender is unable to send arbitrary signals. They have to send anecdotes. And so this naturally introduces some noise into what the sender can say, because the anecdotes have some, distribution with some variance. They also have the sender faces a fundamental gap in the preferences between herself and the receiver. And then there's this potential mismatch between this, the true bias of the scheme that the sender has and the perceived bias from the receiver. Of course, this mismatch will be zero in equilibrium, but the fact that there's a potential for a gap there is helping us figure out what the equilibrium will look like. So in order to make this a little more precise, let me rewrite this sender's utility or cost, if you like, in a way that can help us interpret these three forces. So this is just some simple algebraic manipulations. And what you can see is that there's one component of the sender's cost is due to this signaling cost. So here, what you can see is that there's some variance in what I say, because my posterior is, I can't send my posterior exactly. I can only send an anecdote that's close to my posterior. And so this is inducing one part of information loss. Let me call that the signaling cost. There's a part of my cost as a sender that's due to this gap in our ideal shifts. And then there's a part of the sender's cost that is based on this potential mismatch between the perceived bias of the sender and the of the receiver and the true bias of the sender. And this potential mismatch is what's causing me to pick bias schemes in the first place. I'm trying to reduce my cost by making this gap between the perceived bias and the actual bias higher. So these are the components of the cost. We can now argue that when communicating with anecdotes, the optimal scheme sends an anecdote that's closest to a shift of the posterior. And in order to do that, let's fix an arbitrary scheme, which has some bias, call it delta, okay? And this could be any arbitrary communication scheme. And let's define a communication scheme pi, which is, I'm gonna pick R, the shift of the scheme that picks the anecdote closest to a shift of the posterior. So I'm gonna pick that shift R to be such that that scheme has that bias delta, okay? So I have an arbitrary scheme with bias delta. I have another scheme which is of the class that I'm trying to show you. There is an optimal scheme in that class. And this other scheme, its shift is set such that its bias is delta. Okay, makes sense? Now I can show you that the optimal scheme with that fixed bias delta is going to select an anecdote that's closest to an appropriately shifted posterior. So in order to do that, we can look at this decomposition of the sender's cost again. Since we have some scheme with bias delta, let's put that bias delta into this sender's cost. And what you can see is that the latter three terms, once we fix the bias of the scheme, are constant. And so we can ignore them. And among all schemes with bias delta, the sender prefers the one that minimizes her signaling cost. And that is clearly the one with the shift closest to, with the anecdote closest to this shift of the posterior R. Okay, so this lemma then would prove this theorem, that all we have to think about are schemes that send anecdotes closest to a shift of the posterior. We can then discuss, and I'll have to do this fairly quickly, but we can discuss what the Nash equilibrium and the Stackelberg equilibrium will look like. And now all we have to think about are senders that do this behavior where they try to communicate an anecdote that's close to some shift of their belief. And so in the Nash case, what we'll see is that that shift that the sender is choosing is going to be biased. That is, the shift is non-zero. They're going to actually pick a positive shift. And furthermore, the bias, which is how much, like related to how much I'm shifting, is going to grow as our ideal points diverge or as the number of anecdotes in the system grows. So in order to argue about that, let's see, let's solve for this equilibrium. So now, of course, the sender doesn't know the receiver's scheme. So the fact that pi r equals pi s is an equilibrium condition. Let's look at this cost decomposition again. And of course, this difference, this loss due to the gap in ideal shifts is out of the sender's control. So let's ignore that. The sender is trying to pick pi to minimize the rest. And so let's think about what happens, like what's this persuasion temptation doing for the sender? As the sender, of course, in equilibrium, the pi and the r, the pi s and pi r are equal. And so the biases are equal and this persuasion temptation is zero. But slightly off equilibrium, the sender wants to, because ms minus mr is negative, and the sender wants to increase the last term in this equation. The sender wants to increase bias of pi r minus bias of pi s. And so the sender is going to try and pick more and more biased schemes. In the quadratic term, the third line in the slide is we're ignoring it because it's quadratic, and these are just small deltas off from from each other. So that term goes away, and the third term is the one that is kind of the main force here that is pushing back against the temptation to send more information. So the signaling cost is saying, I want to send information that's as accurate as possible, and so I want the bias to be small, because then I have a denser distribution around smaller biases and I can send more accurate information, so the variance would go down, so I want the bias to be small. And the third term on the slide is saying, well, but I also want the bias to be large, because then the fact that the ideal points, ideal shifts are different hurts me less. And so it's the trade-off between this persuasion temptation and the signaling cost that causes the scheme to be biased in the first place. We can actually even calculate the optimal bias of the scheme as a function of the differences in the ideal points. And so even if you didn't understand the argument for why this exists, I think this result is independently interesting, which is that the sort of bias is determined by the difference in the difference in the sender and receiver's preferences, this MS minus MR. And we can calculate the equation that determines the bias as a function of MS minus MR. And what you can see is that if you fix MS minus MR, so you fix how different the preferences are, then the shift of the communication scheme is, so this R is going to grow as the number of anecdotes grows. So this is 0.2 on the slide. So I'm fixing the right-hand side of the equation. And as I grow the number of anecdotes, I'm getting denser and denser choices close to the true state of the world, and sparse. So in order to get a certain sparsity of choice, a certain R minus bias of R, I have to move further to the tail of the distribution. And similarly, for a fixed number of anecdotes, as the ideal shifts grow, so as I fix the number of anecdotes and I grow the right-hand side of this equality, I also have to go farther into the tail of the distribution in order to hit that particular difference, because I'm getting denser and denser anecdotes. Okay, so what this is saying is that for equal levels of experience, the receiver prefers to communicate with a sender who has similar preferences. And for differing levels of experience, so if there's a sender with more anecdotes than say like an expert versus a novice, the receiver may prefer to communicate with the novice, like in terms of maximizing her utility. She may prefer to talk to a novice if that novice has more similar preferences. That would be better for her utility. And this is going to depend on whether like it's a normal distribution or a Laplacian distribution from which the anecdotes are drawn. But you know, for some priors, we get this kind of result. And so this now brings me back to the open question I had tried to motivate at the beginning, where you're at Thanksgiving dinner and you're trying to decide who to talk to, and somebody knows more about the impact of veganism on the environment, and like somebody else knows less but has more similar trade-offs to you between, like, you know, tasty food and environmental impact, and you get to decide who to talk to. There's sort of a polarization happening naturally, and this is something that I'm interested in exploring more. The polarization here is that, like, I care more about the environment than tasty food, and so does Divya, so I'd rather talk to her even though she knows less about the impact of veganism on the environment than I don't know, Moshe, who cares less about, I don't know, like just some other person who cares more about eating meat. And so that's one interesting set of results. Finally, I will briefly mention the Stackelberg Equilibrium. So in the Stackelberg Equilibrium, the receiver knows the sender's scheme. And so this pi r equals pi s is not an equilibrium condition, but rather a constraint. And because of that, when we look at the cost decomposition of the sender, This is 0. The sender can't do anything to impact it. And this is constant. And so all the sender is trying to do is to minimize the signaling cost. And as we've already said, the signaling cost should be minimized by picking the, like, sort of morally should be minimized by picking the most representative anecdote of my belief. This is actually something we struggled with a lot mathematically. If the sender knew theta, that would be true. But if the sender doesn't know theta, then the anecdotes actually correlate with the posterior belief of the sender. And this can cause difficulties. I'm not going to have time to go through this example, but because the anecdotes can correlate with the posterior of the sender, the closest anecdote to the posterior might not be the most informative one, and so might not minimize the squared loss of the sender. And so that's why we're only able to get this result to hold asymptotically, and we can even characterize the extent to which we need the number of anecdotes to grow in order for the types of schemes we like to be optimal. And so that's the precise sort of asymptotics that we're looking at. And you can see that in the paper, and there's some more like sort of technical conditions around what we need from this posterior.
Nicole, in the Nash equilibrium case, when k goes to infinity, is the bias of R going to 0 also, or I'm wrong?
As k goes to infinity, the bias doesn't go to R doesn't go to 0, but once you debias it, you get much more accurate beliefs as the receiver. Because like the variance is going to 0, say for Gaussians, even though the bias doesn't go to 0.
I see.
And
okay.
I actually, when I was preparing this talk, I was thinking, and this is something I'm not quite sure, I need to explore more, but as the number of anecdotes grows to infinity, I think our model is, I think Crawford-Sobel is a limit of our model. And because as the number of anecdotes.
Yeah, I mean, you get back everything. I mean,
yeah, if I have a continuum of anecdotes, I should be back.
Essentially was in epsilon or something, yeah. You get a.
Yeah, so I need to think more deeply about that connection, but.
No, just yes. The limit should be comparable, should be easier to compare between the Nash and the Stackelberg. I mean, that's why, because they talked about the limit in Stackelberg, that's why I thought about what happens in Nash.
Yeah. The limit in Nash, we should compare to Stackelberg and also to Crawford-Sobel.
Yeah.
So communication with anecdotes, what have I told you? Let me wrap up. And, so communication with anecdotes results in information loss. And that's because, anecdotes are inherently noisy. So that's kind of obvious, but there's less information loss. So I can send more accurate, lower variance anecdotes if I can commit to what I'm going to say. With commitment, the sender is going to pick the most representative anecdote. This is the Stackelberg case. And so not only do I have lower variance, but sort of the discourse we hear in the world would be less biased. But without commitment, the sender necessarily is picking biased anecdotes. And the bias of the anecdotes is, which doesn't mean that the receiver's beliefs are biased, of course. The receiver is undoing the bias in the equilibrium, but the anecdotes themselves are biased, which means, first of all, that because the tail is thinner, there's going to be higher variance. And so we're communicating less information. And furthermore, if I fix the number of anecdotes as the bias is going to grow as our preferences diverge. This is very similar to what Crawford and Sobel observes, that like with higher divergence in preferences, we can communicate less information. And furthermore, if I fix the ideal shifts as the bias grows as the number of anecdotes grows, because I need to target a particular difference between R and bias of R. And so I'm going to go further into the tail. Furthermore, for some priors, receivers prefer to communicate with less informed senders. So this is conclusion of that last statement I said, which then I think leads to a very nice kind of set of questions around social networks, how they form, and information flows and beliefs and actions, and like, do we see polarization due to this kind of force here that receivers might prefer to communicate with less informed senders? And by the way, that force also holds in the Crawford-Sobel model and many other models of communication in Nash equilibrium type worlds. So if you find our model difficult to manipulate, you can go to one of these other standard ones and ask this kind of question about, do we get this kind of polarization and because of communication forces? So I think with that, I am now exactly at an hour according to my stopwatch. So I will pause and take questions if there's time.